analysis topology is almost enough to read it. This one is more advanced. So here you would need to know some amount of manifolds and Riemann integral. But Prin and Stroke is quite nice. Let me start with some basic notions of dynamics. So what is a dynamical system? So informally, it's a system which evolves with time. So there are two cases you can look at. Time is discrete. That means suppose every second, so after 1 second, 2 seconds, 3 seconds, you look at the state of the system. Or time could be continuous. So you look at all positive times and see how the system evolves. The time evolution of the system is given by a deterministic function. So if you're at some point x, say you're in discrete time, then if you're here at time n, then at time n plus 1, you will be at some point f of x. So a discrete time dynamical system will consist simply of a self map f from some space x to itself. So f is supposed to give the time evolution. So a point will go to f of x, then in time 2 it's going to go to f of x, and so on. And this is standard notation. So in n steps you're going to apply f n times, and the effect of applying f n times or iterating the map f n times, I'll just write as f power n of x. So this means f applied n times. So this space x, typically you can think of it as a topological space, and then f would be a continuous self map. But you could also look at other situations where, say, x is a measure space, and then f would be a measure preserving map. Or you could have a situation where the space is actually a manifold, and then f would be a smooth map. So you can look at dynamics in different contexts. So this, when the space is topological, you have topological dynamics. You just have a continuous self map. If you have a measure space with a measure and a measure preserving map, you have measurable dynamics. And if you have a smooth manifold and a smooth map, you have smooth dynamics. So today I'll be talking about some basic examples. So one of the simplest examples you can look at are rotations. So let me look at a rotation of the circle, the unit circle in C. So a rotation by an angle 2 pi alpha. So this would be z goes to e to the 2 pi I alpha times z. So one way to visualize this is, here you have your map. So this is I alpha. So points rotate by an angle. So this is, if you start at say 1, then you're going to move to e to the 2 pi I alpha. This angle will be 2 pi alpha. There's an equivalent way to view this dynamical system. you notice here all you're doing is you're adding 2 pi alpha to the angle, right, that you start with. So an equivalent way to look at this is to consider angles modulo 1. So think of the map. This is Z maps to Z prime, which is e to the 2 pi I alpha Z. Equivalently, you can think of Z as the image under the exponential map of some fraction in the interval 0, 1. So you have the map Z, you write Z as e to the 2 pi I x, where x is in the interval 0, 1. And then Z goes to Z prime in the interval that just corresponds to the map x goes to x plus alpha mod 1. So this will be a map from R mod Z to R mod Z. Okay, so this diagram commutes. Here you have, let's write this as T alpha. So that's translation by alpha mod 1. Right, so looking at the dynamics below is the same as looking at the dynamics above. This exponential map x goes to e to the 2 pi I x. This gives you a homeomorphism between R mod Z and S1. And we say that the two dynamical systems are conjugate. Okay, so let me give a general definition. So if you have two dynamical systems, say x with a self-map f and y with a self-map g, so these are conjugate. So if you have a homeomorphism, say phi, from x to y, so that this diagram commutes. So the action of f on x is the same as the action of g on y. Why are they conjugate? Because this diagram tells you that the map g is the same as, so phi f phi inverse. So they're conjugate. So what, I mean, in the picture what this means is, if you take an orbit of f, so what is an orbit? So orbit of a point, so I will be denoting this by O of x. This is defined to be the set of points f power n x, n greater than or equal to 0. So when you have, so this map phi is called a conjugacy. Phi is called a conjugacy. So in this example, I'm taking x and y to be topological spaces. F and g are continuous self-maps, and phi is a homeomorphism between the two spaces. So when you have a conjugacy, then what you can easily see is that orbits under the first map to orbits under the second map. Right? So in other words, if I take a point, if I look at the orbit under f, then because the diagram commutes, applying f and then applying phi is the same as first applying phi and then applying g. Right? So conjugacy will take orbits to orbits. So when you have a discrete time dynamical system, what you have is actually you have a semi-group of maps. Namely the maps f power n these form a semi-group because if you have f power n composed with f power m, this is the same as f power m plus n. So this motivates the definition of a continuous time dynamical system. So a continuous time dynamical system would be given. So now what you will have is, just like for discrete time, you have this semi-group, the iterates of f, which gives you the dynamical system. So here for continuous time, typically what one takes is actually a group of maps. So phi t indexed by real times t. This will be a group of homeomorphisms which satisfy phi t composed phi s is the same as phi t plus s. Okay. So all we're doing is we're replacing integer times here by real times. So and in this case the orbit of a point x will now be the set phi t of x, t and r. So the orbit will now be a curve. If this is x, this will be phi t of x. The orbit will now be a curve in your diverging space x. So this such a group of maps, this is called a flow. That is a group of homeomorphisms, one parameter group, which satisfies phi t composed phi s is phi t plus s. So what this means is that flowing for time s, flowing for time s, and then flowing for time t is the same as flowing for time s plus t. All right. So,
sir, do
yeah.
you insist that the map r cross x to x is also continuous?
That's right. Actually, yeah. So actually, what this means is you have an action of the group R on your space X, and this map should be continuous. So this is T X goes to phi Tx. You insist that this map it's a continuous action. So that means that this curve, if you fix x, then t goes to phi tx, gives you a continuous curve in x. Okay, so this conjugacy corresponds to isomorphism of dynamical systems. You think of the two dynamical systems as being the same. But there is a weaker notion. So when you look at, say, algebraic structures like groups of vector spaces, you have a notion of isomorphism, but you also have a notion of quotients. Right? You can say when one vector space is a quotient of another, or when one group is a quotient of another. So here, for dynamical systems, there's also a notion of quotients, and that's called semiconjugacy. So semiconjugacy means almost the same, except now instead of asking for a homeomorphism between the two spaces, x and y, you ask for a continuous surjective map. So a quotient of topological spaces. So this double arrow means that the map is continuous and surjective. So let me give you a simple example. For example, take a cylinder and imagine rotations of the cylinder. Right? Then you have a natural projection from the cylinder to the circle. Right? Think of the cylinder as say S1 cross R. This quotient map is just the projection to the first coordinate. So this semi-conjugates rotations of the cylinder to rotations of the circle.
That is a semiconjugacy, right? Where you quotient
No,
realigned by Z.
no, because here I'm looking at R mod Z. So
Right.
this map is a homeomorphism.
No, I mean, if you look at R to R mod Z.
Yes, of
Real
course.
line
Right.
rotation.
So another example is, so yes. So another example would be, this is say example 1, and exactly as you're saying, and like second example would be, so if we have from the circle to the circle, rotation by alpha, then you can lift this map to a map between the universal covers. So it becomes, the universal cover is the real line, right? So this will become a map from R to R, which is just translation by alpha. And this universal covering map, in this case, is the semiconjugacy. That's right. So, okay. So, now let's, right, so I need to define one more thing, which is, so it turns out that what are called periodic orbits often contain a lot of information about the dynamical system. So a point x is periodic. So I'll just write the definition for continuous time, for discrete time. If f power n of x is equal to x for some n greater than or equal to 1, so that means the point comes back to itself in n steps. So then the orbit of x is called a periodic orbit, and the period of the orbit, the period of the orbit is defined to be the minimum n such that f power n of x is equal to x. Minimum n such that n greater than or equal to 1 such that f power n of x. So now let's talk a bit more about the examples of rotations. So for rotations, there are two main cases. One is that the number alpha, the fraction alpha is a rational number, and two is that the fraction alpha is an irrational number. So let's talk about the rational case first. Alpha equal to p over q. So then here it's easy to see that every point is periodic with period q. So here this would be e to the 2 pi I. So applying the map once is just multiplying by e to the 2 pi I p over q. If I apply the map q times, that's the same as multiplying by this number q times. So this will be just 1, right? And if p and q are relatively prime, then the first time when this number raised to power n is 1 has to be q. Right? So all orbits. So this is a very simple dynamics. All orbits periodic of period q. Right? So what is the meaning of this number p here, the numerator? What this means is, so if I have so let me say, for example, p over q is 2/3. So the meaning of that p is, when I look at the orbit, I know it's going to come back. So how does it come back? Well, when I apply it once, I'll come here. This is 2/3 of the total angle. Then when I apply it again, I'll come back here. And I know that when I apply it 3 times, I come back to where I started from. So you can see in this process, we've gone around the circle p times, twice. So p tells you when you come back, how many times you've gone around the circle. Okay, that if you look in the picture of the universal cover, what that means is if I start at some point x, then when I apply the map q times, so the q is 3 here, I'm going to go to x plus p. Right? Because going from x to x plus p means you turn around the circle p times. Right? When I go from x to x plus 1, in this picture I turn around the circle once. So when you go from x to x plus p, you turn around p times. So, all right. Now what happens when alpha is not a rational number? Any idea what the orbit will look like then? The orbit will be dense, right? So then what happens is actually all orbits are dense. So let's quickly sketch the proof of this for those who haven't seen it before. So first note that every orbit, so take any z in S1. Then the orbit of z, so this is e to the 2 pi I k alpha z, where k is greater than or equal to 0. The first thing to note is this is infinite. If alpha is not a rational number, because if 2 of these numbers are equal, I mean if the orbit was finite, then 2 of these points would be equal. So that means e to the 2 pi I k alpha times z would be e to the 2 pi I L alpha times z for some k not equal to L. And that would mean that if I look at e to the 2 pi I k minus L alpha, that would be 1. So that means k minus L times alpha would have to be an integer. So that means alpha would be integer divided by k minus L. It would be a rational number. Is that clear? So the orbit is infinite. So if the orbit is infinite, then you know that S1 is compact. The orbit has to accumulate somewhere. So if you take an accumulation point of the orbit, then you'll find 2 points of the orbit which are very close to each other. So if this is say r alpha power say k of z and r alpha power L of z, then this distance would be less than epsilon. Okay. So, or if you like, better way to say it is that I'll get 2 points of the orbit so that the angle theta between these 2 points is less than epsilon. So let me write it in terms of the angle. So the angle between these 2 points is less than epsilon. So here, without loss of generality, say L is larger than K. Right? These are 2 points of the orbit. Then I can write this as, so this first point, let me call it say W. And the second point is going to then be R alpha, I can write this as R alpha to the L minus K of R alpha to the K of Z. So this would be some R alpha power M of W. So this would be some iterate of our original map R alpha. So this tells you that some power of our map, it becomes a very small rotation, which moves a point by less than epsilon. So now if I look at, so let me call this map, this power of the rotation, let me call this G. This is R alpha power G. Okay. So then the distance between, the angle between W and G of W is less than epsilon. So when I iterate G, what will happen is that I can keep iterating G until the first time so I start from W and then you iterate until you're going to cross a W again. Okay. So that means that all these distances will be the same, say epsilon, and then this last distance will be less than epsilon. So what that tells you is that the orbit of G, every point is within distance epsilon from the orbit of G. But the orbit of G is a power of our original map. The orbit of G is a subset of the orbit of F. So that means the orbit of F, every point is within distance epsilon. So the orbit is dense. Okay. So let me make a definition now, which is common in dynamics. So we say that a dynamical system is topologically transitive if there exists a dense orbit. So the irrational rotation is an example of a topologically transitive system. The rational rotation is never topologically transitive. All orbits are finite, they're never dense. In fact, the irrational rotation it satisfies a stronger property, it's what's called minimal. So let me define that as well. So a dynamical system is minimal if every orbit is dense. So the irrational rotation is minimal. So examples. So why do we use the word minimal? Because you can show that, so here's a aside, so minimal implies the following. The reason why we call it minimal is because you cannot break the dynamical system down into a smaller system, into a union of smaller systems, in the sense that if you take any closed, so if let's say K, if this is a closed invariant, K non-empty, closed subset which is invariant, so invariant means f of K contained in K, then K must be the whole space. So this is why it's minimal. That is, the smallest non-empty closed invariant subset is the whole space itself. If you had a non-empty closed invariant subset, then you can always restrict the dynamics to that subset. You get a smaller dynamical system. Here it does not have any such smaller dynamical system sitting inside. So this is, you can prove this as an exercise. Exercise. Okay, so why do we say that the system is topologically transitive if it has a dense orbit? Well, essentially that means if you have a dense orbit, then given any two open sets in the space, U and V, you can go from one to the other using the dynamics. So let me make that a bit more precise. So here's a little proposition. Suppose X is locally compact, say separable metric space. And suppose for all UV non-empty open subsets of X, for all capital N greater than or equal to 1, there exists a little n greater than or equal to n such that f power n, let me write it like this. So U intersect f power minus n of V is non-empty. Then F is topologically transitive. So what does this condition here mean? U intersect f power minus n of V non-empty. This means there exists a point which is in U and which is in f power minus n of V. Being in f power minus n of V means that f power n of x is in V. So that means there is a point in U which maps under f power n to V. So this condition is saying that no matter what two open sets you take in your space, given any large time n, you can always find a time after that where starting from U, you will enter V. So this implies that you have actually a dense orbit which, let's prove that. So the proof is not difficult. What you can do is the following. So here's the proof. So we're assuming our metric space X is locally compact and separable. Separable means it has a countable dense subset. Locally compact means every point has a compact neighborhood. So this implies that X is second countable. So X is second countable. So second countable means there is a countable basis of open sets for the topology. So let me remind you what that means. That means given any open set, there given any point and an open set containing that point, there exists an element of this countable family Un which contains the point and is contained inside the open set. So this is called a countable basis for the topology. And what is the point of taking a basis for the topology? Well, if this is our space X and these are our UIs, say this is U1, say this is U2, U3, then because this is a basis for the topology, a sequence is dense in the whole space if and only if it intersects every UI. Okay. So now all we have to do is construct a sequence which intersects every UI. So for that we use this hypothesis that you can go from any U to any V using the dynamics, right? So we can always assume first of all, that U1 closure is compact, okay, because our space is locally compact, so we can take a basis set which is contained inside a compact neighborhood, so its closure is compact. Now we know there exists so we know that U1 intersect some f power minus n1 of U2. This is a non-empty open set, right? So we can choose inside this some non-empty open set V1, okay, whose closure is compact. V1, because it's contained inside U1, so V1 closure is compact. So here inside we choose some V1. Now we want to, starting from V1, now we want to go to U3. So we choose, so we look at V1 intersect f power minus n2 of U3, and this again will be non-empty by our hypothesis, and we can choose n2 bigger than n1. Okay. So inside this we'll find some V2. And now you can see what to do, right? You inductively define a nested sequence of sets, V1 containing V2, containing V3 and so on. Right? So that, so say Vk plus 1 is contained inside Vk intersect some f power minus nk plus 1 of u, what is it, k plus 2, right? Okay. So now you look at the decreasing sequence of compact sets, Vk, closure. So this is a nested sequence, so this is, the intersection will be non-empty, so there exists some x in the intersection, and then by the definition of these Vk's, f power, I guess, nk of x belongs to uk plus 1 for all k. So that means the orbit of this point in the intersection is going to visit every basis set, so it's going to be dense. Oh. So now we can ask for, so later as we go on in the course, I'll get to systems, well in this class itself, we'll get to systems which are what may be called chaotic. So far the systems we've seen are just rotations and translations. So rotations are certainly not chaotic, in the sense that if you take 2 points which are nearby, then rotations are isometries. So when you apply your rotation, if the 2 points start close together, then they will always stay close together. So orbits are stable under small perturbations. If I change my initial condition a bit, the orbit still stays close to the original orbit. For a chaotic system, one would expect sensitive dependence on initial conditions. So if you change the initial condition slightly, then the orbits should diverge significantly in the future. So yeah. So let me make a definition first. This is something I'll be talking about throughout the course. Something called topologically mixing. So this is intended to capture some feature of chaotic dynamics. So we'll say a dynamical system is topologically mixing if for all UV non-empty open sets given any time n, then no sorry yeah, so actually you don't have to say. So there exists a time n which depends on the two open sets UV such that for all times little n bigger than capital N, f power, so u intersect f power minus n of v is non-empty. So let's try and understand what the difference between these two definitions is. So topologically transitive was saying essentially this: given two open sets u and v, if I take any time, then I can always find some time bigger than n where I go from u to v. Now this is saying given any u and v, I can find some time n such that for all times, so the key point is all, for all times after time n, there will be some point going from u to v. So see, this fails for the irrational, for the rotations, because even for an irrational rotation, what happens? Suppose I take a u and a v here, then I know that the orbit is dense. So suppose I take these u and v small compared to the angle by which I am rotating. Right? Then what's going to happen? I know there will be infinitely many times where I enter enter v starting from u, but that will only be some subsequence of times. That's not going to happen for all large times, because as soon as I enter, if this v is small, then after time 1 I'll again go out of v, and then it will take some time before I come back into v. Whereas topologically mixing is saying what should happen? For all times after large enough, I'm always going to end up, there will be some point in u which lands up in v. So I've made a definition. Let me give you an example. Right? What's an example of a topologically mixing dynamical system? Why is it called mixing? Let me give a picture, because what this means is the following. Suppose so this is my space X, and suppose I start from some small, very small part of the space U, non-empty open, and suppose I take two sets, some V1 and a V2, right? Then what topologically mixing is saying, this pair U comma V1 is going to give me some N1, so that for all times n bigger than N1, I will have some point which goes from here to here, from U to V1. And similarly, I'll get some N2 so that for times bigger than N2, I'll go from U to V2, right? But now I know this is true for all times bigger than N1 and N2. So if I take any time bigger than the maximum of these two, right? Then for any such time, there's going to be points both starting in U. One goes into V1, the other goes into V2. V1 and V2 can be anywhere. So in this sense, it's mixing. You start from some small open set that is getting spread out over the whole space. See, if I can take finitely many such VKs spread out all over the space. So then there are going to be points. I'll get some times n1, n2 up to nk. If I'm larger than all of those times, then there will be points whose orbits at large times will diverge, you see. One is going here, the other is going here, the other is going here. So it's mixing. Is this, it's like cooking. Okay, so,
Sir,
yes?
there
Yes?
In that proposition, why are we interested in sort of backward images?
No, because, well, what this means is that, let me say that, what does this mean? This means there is a point in U which is also in f power minus n of v. F power minus n of v means that f power n of x belongs to v. So that's why we're interested in backward image, because this tells you that starting from U, I have a point which is in U and which after n steps goes to v. That's why I'm looking at this set. This is the set of points in U which move to v after n steps.
We can say other way around, right? Fn of U intersection v is on it.
No, yes, sure. Yeah,
Uh,
yeah,
why
it's the
to
same
put
thing.
that
You're right.
negative,
Yeah. F power n of U. Yeah, sure. It's the same thing. I don't know why. Yeah, I'm writing with F power minus. It's the same thing. You're right. That's right. F power n of U intersect V is not.
Or
Same.
maybe because backward orbit becomes always bigger and bigger, something like that.
Maybe.
Because forward orbit,
Well,
left is
like
constant.
if you look at this proof, then it makes sense to look at backward orbits, because you want to construct a nested sequence. So then you want to look at the same starting point. So you look inside, yeah, U. Then it makes sense to look at backward orbits. Okay, so let me give you an example of a topologically mixing system. It's very simple. So here's the example. It's simply the map. Z goes to Z squared on the unit cell. Just the squaring there. It's very simple. So again, we can look at this on S1, or we could also look at this on R mod Z. So on R mod Z, what is this? Here you write Z as e to the 2 pi I x. So Z squared is what? This is e to the 2 pi I 2x. Right? So all that means x is what? It's just the angle. Right? So what this is doing, it's doubling angles. Right? So from R mod Z to R mod Z, this is just the map. So here x goes to 2x modulo 1. Right, so this is the angle doubling map. So these two are conjugate, and if you want to understand the dynamics though, well, first of all, it's easy to see this is topologically mixing. Why? Because you take any open subset of S1, or you can think of it as a subset of R mod Z, then say, so U is non-empty open. So U is going to contain some interval, so let me think of it as in R mod Z. So U is going to contain some interval of the form, some closed interval which is bounded by rationals of the form k over 2 to the n and k plus 1 over 2 to the n. Right? So if I take this interval, this is an interval of length 1 over 2 to the n. What happens under the angle doubling map? The length of the interval gets doubled. Right? Each time I apply f. So if I call this interval j, then if I look at f power n of j, this is going to be the whole, this is going to be all of R mod Z. So that means for time, let me write this as a capital N. Capital N. So then that means for n greater than or equal to n, f power n of u is all of R mod z. So this of course intersects every v. It's the whole space, so it intersects every point. So this is easy to see, it's topologically mixed. But we can say much more about the dynamics if we understand that angle doubling is what? X goes to 2x. Well, if you write x in binary, right? So it's just a sequence 0 point, some 0, 1, 0, etc. A sequence of zeros and ones. In binary, multiplying by 2 just means shifting the binary point. Right? It just means shifting one digit. So what that means formally is that writing in binary means the following. You take this space, the space of all zeros and ones. So you have this space, 0, 1 power n. This is the space of sequences of zeros and ones. So this is a compact space with the product topology. So in fact this is a Cantor set. This is a Cantor set. So here you have the map called the shift map, sigma, which sends a sequence. So I'll just write it as, so say A1, A2, etc. This maps to A2, A3, etc. So it just shifts the sequence by 1, forgetting the first coordinate. This is called the shift map. And now what you have is a semiconjugacy between the shift map and this angle doubling map, which just sends an infinite sequence to the real number which it represents. So that map is, so if I call the sequence say A bar, then my semiconjugacy, my x is going to be summation an over 2 power n. N goes from 1 to infinity. This is my semiconjugacy. You can see this can't be a conjugacy because this is a Cantor set. This is totally disconnected. So it's not homomorphic to the circle. So what happens is you have a quotient map from this Cantor set onto the circle. Okay. So if you want to have a picture of this space, what you can do is the following. Infinite sequences of zeros and ones you can represent by a tree. So you start with a vertex, and then if you have a 0, you move to the left. If you have a 1, you move to the right. So finite sequences of zeros and ones are going to be represented by finite sequences in the tree, and then an infinite sequence of zeros and ones. What happens is you imagine the branches of the tree getting smaller and smaller, and sort of, well, infinite sequences of zeros and ones corresponds to infinite paths in the tree. Those will give you a Cantor set in the middle. So in some sense, this Cantor set is the boundary of a tree. Anyway, I don't want to get into that more, but this is one way to visualize this space. Okay, so good. So what is the use of this semiconjugacy? This tells us many things. For example, if I look at the shift map, I can see that the shift map has many periodic points. Because if I take any periodic sequence, so say A1 up to some AN, and then I repeat this, right? This is going to be a periodic point of period n for the shift map. Right? When I shift this sequence n times, I get the same sequence. It's just a recurring sequence, a periodic sequence, right? So if I look at the real number which this gives, then this goes to some x, which is periodic for the angle doubling map, right? It has a periodic binary expansion. So when I keep applying the angle doubling map, I'm going to get a periodic point for the angle doubling. But now, if I look at any point on the circle, I can always approximate it by points which have periodic binary expansion. Right? What do? I take the binary expansion of my point, then I go up to some large n, I truncate, and then I replace the tail by a periodic expansion. So that's going to give me a point which is close to this point. So what this means is that periodic points are dense. So periodic orbits but note that, see, topological mixing clearly implies topological transitivity, right? Because topological transitivity was for there exists an n larger than some n, right? Here you have it for all n. So topological mixing implies topological transitivity. So that means you have a dense orbit, right? So you have dense orbits, but at the same time you also have periodic orbits which are dense. So this should give you some idea that there is a rich structure to the orbits. That is, I am going to find points which are periodic, so they come back to themselves. But then near such a point, I will always find another point whose orbit is dense. So it's never going to come back. It's going to keep going around. So under a small perturbation, a finite orbit will turn into a dense orbit. So you see there's some chaotic behavior here. Right? The orbits are right. So a small change in the initial conditions is going to change the behavior of the orbit completely. Right? I can start from a periodic point. Near a periodic point, I'll find the point whose orbit is dense. So this is a typical example of a chaotic system, and the reason for the chaotic behavior is the fact that the map is expanding. Expanding means locally distances are multiplied by a factor 2. Distances are increased by some fixed amount. So this expanding behavior is going to be a feature of the systems we are going to talk about.
Every sufficiently nice topological space is a quotient of a candidacy. So can we from the
that is, I don't really know a proof of that, but I don't know, how nice do you have to be?
I think.
I don't know how nice. You're right, there is some such universal property of the
Right.
candidacy.
So can from a topologically mixing map on
So-
the candidacy, can we get it on arbitrary?
No, in the sense, it has to be, the dynamics has to be compatible with the quotient relation.
I see.
So here, right, this diagram has to commute. So that means the dynamics has to preserve whatever quotient relation you have. That relation has to be preserved. But it's true in the sense that this universal property of the Cantor set, it does come up in dynamics in that many systems which are expanding, so which have expanding behavior, they do admit a semi-conjugacy from a Cantor set onto the dynamical system, and the map becomes just the shift map.
I see.
The only difference is from most dynamical systems, you will not get the whole Cantor set 0, 1 to the n, and it may not. You will, in general, have some finite alphabet.
I see.
So 0, 1, 2, 3, say k power n, so k symbols, and you will not have the whole symbol space. You'll have some shift invariant closed subset of that. So that's a whole topic in itself called symbolic dynamics, which uses things called Markov partitions and so on. I won't get into that at all. But it's very closely related to the systems I'll be talking about. Okay, so now let's look at a first example of a continuous time dynamical system. So a continuous time dynamical system, the simplest non-trivial example would be in 2 dimensions. Right? In one dimension, you just have a line, and any orbit will be the whole line essentially, unless it's a point. So the simplest example we can look at really is you take the two torus, so R2 mod Z2. So here you have, so let me draw a picture in the universal covering. So this is the universal covering. And so each square here maps once onto the torus. This is R2, this is torus, this is D2. And now the system I want to look at is, well, in R2 it's going to be a flow, so I have to give you a one parameter group of transformations. So what you do is you choose a non-zero vector omega, okay, omega in R2 non-zero. So this is the direction, and then you look at the flow which moves you parallel to the direction omega. So that means x goes to say x plus t omega. Okay. Right. Now these are transformations from R2 to R2, which give you a flow on R2, but they also respect the quotient relation. That means if I change x by an integer vector in Z2, then the image also gets changed by an integer vector. So therefore they descend to maps of the torus. Okay. So what happens is you have these orbits which are straight lines parallel to the direction omega, and these will give you curves below in the torus, so, which will wind around some number of times. So I want to talk a bit about this flow. Okay. So here it turns out this is closely related to the irrational rotation in one dimension. So this is called the linear flow on a torus. Okay. So this is the group of maps, x in R2 mod Z2 maps to x plus t omega in R2 mod Z2. Okay. This is called the linear flow on torus. And this is closely, so if I write omega as a vector, say in alpha 1, alpha 2, okay, then the dynamics of this flow is closely related to the number alpha, which is the slope of this vector. So alpha 2 over alpha 1. Okay. This is the slope of these lines, right? This is the slope. And it turns out to depend on whether alpha is rational or irrational. Right? So if you have a rational slope, what happens? That means if I start, let's say I start at a vertex point, and suppose the slope is p over q, right? So that means when I q directions in the horizontal, I'm going to move up p in the vertical, right? And I'm going to come at a new lattice point, say, well, in this picture, say I'll get p is, so q is 2 and p is 3. Right? So 3 by 2. Yeah, so what does that mean? That means in the torus, since I'm going from one lattice point to another lattice point, in the torus my curve will close up. Right? So what will happen is all my orbits below will be periodic. So, and the orbit is going to, so if you look at these two curves below, the horizontal and the vertical, they give you the two generators of the fundamental group here. Right? And these, so one is, this is the vertical curve, this is the horizontal curve. Right? The fundamental group is generated, it's Z2, generated by this curve and that curve. And if this is P over Q, so if alpha is, that's case 1, alpha is P over Q, then that means all orbits are going to be periodic. So that means they're going to be closed curves. Okay? So all of these curves are going to close up, and once it closes up, it gives you a loop, an element of the fundamental group. That element of the fundamental group is going to be given by Q times the horizontal plus P times the vertical. Okay. So this is the easy case.
It will be PQ naught. Right.
Right.
So
Yeah.
this is-
That you call that a PQ naught, right?
Right.
Yeah. Sure. PQ. So it just means P plus Q in the fundamental group. P times A plus Q times B. Okay. So here, this is a nice situation. But now what happens when alpha is not a rational number? Well, then here we would expect that every orbit would become dense. Right? How do we see this? So in this case, all orbits are going to become dense. So here's a nice construction which is going to relate this directly to the rotation. So there's a way to relate this flow on the torus that's in 2 dimensions. That's a continuous time dynamical system in 2 dimensions. You can relate this to a discrete time dynamical system in 1 dimension lower, in 1 dimension. So what you do is the following. You have the torus. And so you have your line, right? Your torus is foliated by lines parallel to the direction omega, these curves parallel to the direction omega. You take this vertical circle. Okay? This is going to be transversal to all these orbits. Okay? So it's what's called a global cross section to the flow. So that means a transversal, a submanifold which is transverse to all the orbits. Okay? So what you can do is look at the first return map to this cross section. So this is going to go around the torus sometime, right? And at some point it's going to come back and hit this transversal again. Okay. How do we see this? Look at this in the universal cover. So in the universal cover, this vertical circle lifts to the y-axis. Okay. What are you doing? When you're going this way, you're basically looking at the first time you come back to, this is another lift of this vertical circle, right? Both of these curves project to the same, both these lines project to the same vertical circle. What you're doing is you're starting from the vertical circle and then from this line and looking at the first time you come back. That will be this point here, right? So this point is the same as this point. Now what is this point? Well, this distance is 1 and the slope is alpha, so that means this distance is alpha. So that means when you come back to this vertical circle, what have you done? You've moved by alpha. So on this vertical circle, the return map to this circle is the rotation by alpha. So this is called, this return map construction goes back to Poincaré. So Poincaré did this for general systems. It's a very useful technique to reduce the dimension of the system, because you've gone from a 2-dimensional system now to a 1-dimensional system, right? And from continuous time to discrete time. So it makes life easier. So the return map to the cross section is just our familiar rotation. This is the return map. So what happens? Now you look at this curve. So that means as you keep going along the orbit in the torus, you'll keep returning to this cross section at iterates under the rotation. But alpha is irrational, so you know that these iterates are going to become dense. Right? So here you're going to hit this cross section in a dense set. What does that mean? That means if I look at the curve, its lifts above, its lifts are going to hit the vertical axis in a dense set. So that means the collection of lifts is going to become dense in R2. When you project, you just get the one orbit below. It's going to become dense in T2. So for this linear flow on a torus, you get, again, this is a minimal dynamic system. All orbits are dense. All orbits. And this follows from minimality of the return map, which is the irrational rotation. So this is again nil. Okay, good. So why was I talking about this linear flow on a torus? Again, this is not chaotic. This is again a flow by isometries. These preserve the standard flat metric on the torus, right? These are just translations. On R2 they preserve the metric on R2. So on the quotient they preserve their isometries. This is not chaotic at all, but it is related to a certain chaotic map. So now I'm going to spend some time on this example. So these are what are called hyperbolic toral automorphisms. So I'll be spending some time on these maps. So what is a hyperbolic toral automorphism? It's a long name, but it's a very simple thing. You take the torus, the two torus. You can do this in higher dimensions too, but what you do is you take a linear map A with integer entries and determinant 1. Okay, a 2 by 2 matrix in SL2Z. And you assume that assume that it's diagonalizable and neither of the two eigenvalues have modulus 1. So then we say that A is hyperbolic. So A hyperbolic if eigenvalues, so it's diagonalizable, and well, in this let me assume that you don't have to take it to be diagonalizable always, but let me take it to be diagonalizable. And eigenvalues do not have modulus 1. Do not have modulus 1. So, the well-known example, which was first looked at by Arnold, so this has a name in the literature. This is called Arnold's cat map. Just take 2111. It's called the cat map because apparently Arnold drew a picture of a cat on a torus, and then applying the map many times, the cat became very distorted. Anyway, take this. You can find the eigenvalues and check that neither have modulus 1. Okay. Right. I should say when. Right. So what is the dynamics? Well, see. Your linear map, A goes from R2 to R2, but because it has integer entries, it sends the lattice points to the lattice points, right? Because it has integer entries. So therefore it descends to a map from the quotient R2 mod Z2 to R2 mod Z2, right? So again we have a semiconjugacy. So let me call the map below T. Okay? So this is from T2 to T2. So here what happens is you have two eigenvalues. So say A V1 is say lambda 1 V1 and A V2 is lambda 2 V2. Where let's say mod lambda 1 is less than 1 and mod lambda 2 is bigger than 1. Right, you see, since we're taking something with determinant 1, the product of the eigenvalues is 1. So that means if neither of them has modulus 1, one has to have modulus less than 1, the other has to have modulus bigger than 1. Because the product is 1. So, what happens? Well, you can see for this linear map above in R2, what does this linear map do? If I take things in the direction of V1, right, the lines parallel to the direction V1, then on each the map A acts like a multiplication by lambda, like a scaling by a factor of lambda 1. Right? So lambda 1, mod lambda 1 is less than 1. So that means each of these lines, so this foliation of R2 is preserved. Each line here goes to another such line, but distances are contracted. So if 2 points are far apart here, then they'll become close here, because mod lambda 1 is less than 1. While if I take the transverse foliation parallel to the direction V2, right, then again this transverse foliation is preserved, but now points which are close together are going to be expanded far apart, because on each line it acts like a scaling by a factor of lambda 2, which is bigger than 1. So what you have, if you look in the torus, then you have these two transverse foliations. So we have two transverse foliations. So these foliations are called the stable and unstable foliations of this map. Okay, so the stable ones, so this are denoted WS, S for stable. This is the stable foliations. So that would be the curves which are parallel to the direction V1, where distances are contracted along the leaves. And similarly you have the unstable foliation, where distances are expanded. Okay. Now, you can easily check for this map that the slopes of these two vectors are irrational. Okay. The slopes of these two vectors are going to be irrational. So, well, that's a simple calculation. I mean, let me just do it for you. So you have 2, 1, 1, 1 times, let's say the vector, take an eigenvector, say xy. So this is some lambda xy. Yeah, so what you do is look at the ratio. The slope of this vector will be the same as the slope of this vector. So this gives you 2x plus y over x plus y equal to x over y. Yeah, and write x over y equal to alpha. So this is alpha. And then divide by y here. So this becomes 2x over y plus 1, x over y plus 1. So this means this is 2 alpha plus 1 over alpha plus 1. And so then you just get a quadratic equation. So alpha squared plus alpha minus 2 alpha minus 1. So alpha squared minus alpha minus 1 equal to 0. And so this means alpha is equal to 1 plus minus square root 5 over 2. So these are irrational numbers. So both the slopes are irrational. What does that mean? That means each leaf of this foliation is dense. These are irrational. Well, what does this tell us about the dynamics? Well, we can easily see two things. One is the dynamics is again topologically mixing for this map. Why? So I'll give you the idea and a sketch of the proof. It's very simple. Yeah. So here's the little proposition. T from the torus to itself is topologically mixing. So proof. Well, what's the idea? It's very simple. You have your torus and you're taking some open set U and you want to show that it intersects a given open set V. Okay? So you have a U and you have a V, and you want to show that for all time large enough, T power n of U intersects V. So what do you know? Well, you know that inside U, you can find a small piece of unstable foliation. Right? You can find a small leaf of the unstable foliation, small part of a leaf. But now you know that, so say you have some, say L, which is inside, let's say this, I take a point P here, take a point P. So this is inside the, inside the unstable leaf passing through P, which is inside. L contained in U. Okay, but now what's going to happen? You know that as you apply the dynamics, this is going to go to other leaves of the unstable foliation, but each time the length is going to be increased by a factor mod lambda 1. So eventually what's going to happen? You're going to get a very long segment of unstable leaf, as long as you want. But now you know that every leaf of the unstable foliation is dense. So if I have a long enough segment of unstable leaf, it's going to intersect V. So as soon as I have time is large enough, right? So T power n of L for n bigger than or equal to some capital N, the length of this is going to be bigger than some R for all n, right? After some point it has length uniformly bigger than some R. So all you have to show is that if you take any segment of unstable leaf of length greater than or equal to R, so given what you have to show is the following, you can easily do this as an exercise. So given epsilon positive, there exists R depending on epsilon such that for any segment of unstable foliation of unstable leaves of length greater than or equal to R, such that any segment L of unstable leaf of length greater than or equal to R intersects every ball of radius epsilon. Okay, so any long enough segment of the unstable foliation is epsilon dense in the torus. So given an epsilon, you can find an R, so that any segment of length at least R is epsilon. So that's it. So you just choose a small piece of unstable foliation inside your open set U. Then you know for all large enough times, it's going to be of length at least R, so it's going to intersect V. Okay, so I'll stop here.